So, welcome everyone to this master class by Professor Thomas Brüstle from Sherbrooke University. I mean, one of the identities of him I should mention. Yeah, he's a leading figure in the research in this area, of course, but he was also a student of Gabriel, uh, the theorem that you saw in the first week, Gabriel's theorem. So, and I think this is for the first time in the history of NCM organized schools that a foreign speaker is giving lectures. So I'm very happy to present Thomas. Over to you, Thomas.
Okay, thank you very much, and it's an honor to speak, to give this lecture series, and it's even more an honor if you say it's the first time that somebody from outside India is giving this lecture. I'm very happy, and I'm very proud to have some connections to the community of mathematics in India, and I'm looking forward to come to India myself next year, where we are organizing a workshop at Chennai. So I see this school a little bit as a preparation for that school. So I am from, oh, by the way, Sherbrooke, you spell with an S, with an E. Okay. So I'm from Canada, and the time zone of Canada and India, they do not match very well. But I am currently in Europe. I'm at my parents' place, so this is much better in terms of time difference. But I kind of need to adjust my setting a little bit, yeah. And plus, it's very cold in Europe, and I have a little bit of a cold, so I hope I can deliver my lecture for 90 minutes. For this reason and other reasons, I wanted to go a little bit slow today. Also, I believe you had already 2 full weeks, 2 weeks full of lectures, and it's kind of getting a lot. So in the third week, I try to start kind of easy pace, and you can interrupt me if you have questions anytime. And I'm a student of Gabriel, as Amit mentioned. And Gabriel had, when he was a great teacher, I would say, but he had the pleasure to ask questions to the audience. He would insist to ask questions, and we were sitting in a lecture room, and he would ask a general question, what did we do last week and which theorem? And then he would ask, so who can remind us how do you prove that theorem? And then of course all the students were hiding behind their neighbor or something like this. And then he would pinpoint, like, you say something. And this was a very difficult moment. I will not do that, but I want you to participate, and if you don't, then I will start asking questions. This is what I learned. Okay. So don't be intimidated. There's no wrong or right answer. We are discussing, and that's all very good. Okay. Also, I would appreciate if I see some of you on screen. I see Amit and Isha. This is very appreciated. If some more of you would like to show their face, in particular, if they ask a question, I would be happy. Then I'm speaking to some actual audience. This makes it easier. Okay, good. So we have this is part of that school which deals with representation theory of quivers and the BGG category O for semi-simple algebras. I am more on the representation theory side, on the quiver side. In fact, my mathematical education, so during my PhD, was really quivers and quiver representations. This is what I learned from Gabriel. But you learn there are close connections to semi-simple algebras, and I would like to address those as we go along. Okay. And so this lecture series is broadly announced as recent trends in quiver representations, but we particularly have two topics that we want to discuss in more detail. One is cluster algebras, and the other one is gentle algebras and their geometric models. So I will start today with cluster algebras. And maybe the first 3 lectures will be devoted to cluster algebras, and then we slowly move over to general algebras and geometric models. General algebras are a particular case of string algebras, which Amit already presented last week, but I will recall all the properties, all the definitions that we need. Okay, so let me move on. So we start with the part on cluster algebras. Um, Cluster algebras have been
Sorry,
created,
uh,
found,
so,
yes.
sorry. Yeah, can you please enlarge your screen? I mean the thing is very small. I can't read.
You want to read those things?
Oh, yeah. I thought
Yeah.
it's part of your presentations. Okay, yeah, but
Yeah, that is not really important. The important part that you should be able to read are those big
okay.
notes. Can you read that?
Yeah, yeah. At the
Okay,
moment,
this is
yes.
perfect. So here I gave only a little. Okay, so cluster algebras were invented by Fomin and Silivinsky around the year 2000, and I just wanted to illustrate the tremendous success of that story by. I went to Google Scholar and I went to the Google Scholar page of Sergei Fomin, and you see the details here are not very important to read, but Fomin and Selivinsky wrote together a series of papers. So there's Fomin and Selivinsky, they wrote a paper, Cluster Algebras 1, 2, uh, 3, and 4, and some other papers. And those papers were published in really high rated journals, and the part I would like to point out is the citations. So the first paper has been cited almost 2,500 times, which for mathematics is an incredible high number. I mean, they have those numbers in theoretical physics or in machine learning, but for mathematics, this is really an amazing number. 2,500 articles have appeared since 2000, and they give reference to the first paper, Cluster Algebras 1. So this is a tremendous success, and by now, you know, the AMS, American Mathematics Society, has subdivided mathematics into certain disciplines, and since around 10 years or so, they created a new discipline called cluster algebra. So this is now its own research subject. So I wanted to give you present you the two people, Sergei Fomin and Andrei Zelevinsky, who created this theory together. And they invented cluster algebras. I borrowed the word invented from the uh, survey paper of Bernhard Keller. Bernhard Keller wrote several survey papers on cluster algebras, and in one which is entitled Cluster Algebras and Derived Categories, he speaks about the invention of cluster algebra. So this is a philosophical question. Mathematicians, do we create, do we invent, or we just find things that had already been there? So I borrowed the term of Bernhard Keller. They invented cluster algebras, and their goal was to study uh, things which are called canonical bases or total positivity in certain algebraic varieties, in certain flag varieties. I will not go into the details of this. Canonical basis comes from Lustig's theory of canonical bases, and this is vaguely related to the other topic, BGG category O. And that was the original goal. And nowadays, cluster algebras have been related to all sort of different subjects. I list a few. There's something called Poisson geometry. There are discrete dynamical systems. There's higher Teichmüller theory, Stashev associahedra, stability conditions, Donaldson-Thomas invariance, and representation theory of Quivers. And among all those topics, I am certainly not possible to cover those, but I will really focus on the last part, the representation theory of Quivers, and illustrate how the definition of classical algebras is related to the representation theory that you learned already in the first week. So this is the main goal of my lectures here. First, I want to give you the definition of cluster algebras, and then starting tomorrow, we will relate it to quiver representations, the representation theory of quivers. Okay? Good. So this is also not very important. Before we start, the definition of a cluster algebra is kind of complicated. It is defined, and Bernhard Keller gives a kind of an overview description, so that one here is not an actual definition. We will arrive at the actual definition later, but it builds on several techniques that I need to introduce first. And as a general description, Bernhard Keller says a cluster algebra is a commutative algebra over the field of the rational numbers. And in the cluster algebra, you find a distinguished set of generators. They are called the cluster variables. So these are one of the things that we have to define. The cluster variables, they are grouped together into sets, which are called clusters. Those sets, they overlap. They are not disjoint. So, and there will be a procedure which is called mutation that allows us to take one cluster from one set and move it over to another cluster variable from the other set. So these are the terms that we need to address today. I will start with mutations, and then based on the notion of mutations, eventually we will define clusters and cluster variables. And then at the end of the day, we will have the full definition, which is kind of a complicated recursive definition. Yeah. So let's start from there. What's the real, just to say this right from the beginning, what is the relation to Lie algebra between cluster algebras and Lie algebra? This can be seen in the following theorem. The cluster algebras are given by sets of variables, cluster variables, and that set might be finite or infinite. Yeah. And among all cluster algebras, those having only a finite number of cluster algebras, they are really in bijection with finite root systems. So this is our connection to the other half of the lecture series, where you have finite root systems. The finite root systems give exactly the classification of those cluster algebras having only a finite number of cluster variables. So in a sense, this is an analog or a generalization of Gabriel's theorem. Yeah, Gabriel proved the theorem that a quiver is representation finite if and only if it is a quiver of a Dünkin type, ADE, and the Dünkin types, ADE, appear in the classification of finite root systems. And this kind of extends that theory to all root systems, and the analog is then the finite root systems correspond to finite type cluster algebras. So this is just some motivation for the start. These two subjects are related. And now I wish to go into the definition. So to start
Can I
with the
ask
definition,
this? Like,
yes.
Only the singly laced root systems appear here, ADE, or also other ones?
All of them.
All of them. Okay. Okay. Thanks.
But they are a bit more complicated. I will start with this simply laced ones, and then I will move on to general root systems.
Okay.
Yeah. And I will address the issues that we have along the way. So to start the whole procedure, we have to introduce that, what they call mutation. Okay, so I want to introduce from the context that we are comfortable with so far. I want to start with quivers, because you studied quivers now since 2 weeks. And I assume you're comfortable with the notion of a quiver, and I want to start from that perspective going into the theory of cluster algebras. So we fix a quiver Q. Q will always denote a quiver in my lectures. And I do assume, so very important assumption, I do assume that my quiver has no loops and no two cycles either. Yeah. So two cycles would be a pair of arrows, one going from I to J and the other one from J to I. And we do assume that such a two cycle does not occur in. Sorry, it's my parents' phone ringing. It will stop after some while. So the quivers I'm considering have no loops and no two cycles. From now on, without any further saying, I assume all quivers satisfy that. Okay? Good. Can you give me a thumbs up? Yes, that's what we assume from now on. Thank you. Okay, good. So I'm going to present you the notion of a quiver mutation not in the way Fomin and Zelewinski gave it in their first paper, but really coming from what you already learned in week one. In week one, uh, we defined the reflection of a quiver. So by the way, the set of vertices of my quiver, I will always label them by the numbers 1 to up to n. Okay, so the set of vertices is 1 to up to n. And when we choose one such vertex k, in week one, you learned, we defined what is the reflection when k is a sink, right? So the first operation was reflection in a sink. What was the reflection in a sink doing? We just reverse the arrows which are adjacent to that point, to that vertex. Okay, and there's also a reflection at the source, which is dually when k is a source, then we same thing, we reverse all the arrows that are adjacent to that source. So in week one, you defined those reflections. However, if you go to the other side of the story, if you go to Lie theory and root system, there's a notion of a while group, and the while group W is generated by reflections sigma k, where k is any vertex. K is any of the numbers 1 to n. So in Lie theory, they do allow reflections at each vertex, at any vertex. However, what did we do in week one? We consider reflections only at sinks or sources. So something is missing, and you might ask yourself the question, what happens if we apply something like a reflection at a vertex of the quiver which is not a sink or a source? Yeah, so let's analyze that situation a little bit. Assume we have our quiver, and let's say we have a vertex k, which is not a sink and not a source. What does that mean? There's a path from some vertex I going through k and ending in j. So this k is not a sink and not a source. So what would happen if we were to define a reflection sigma k at this vertex? Yeah, I mean you would certainly want to flip the arrows. You would certainly want to change the orientation of the arrows which are adjacent to that vertex k. But see, if we do just this, then we lose important part of the information. I mean, in general, I will be just some part of the quiver, so there might be some other arrows going into I, and there might be some other arrows leaving J. And you studied the path algebra of the quiver, so there are paths coming from some vertex X and ending in some vertex Y. Can you see this? When I write, yeah, and some paths starting in a vertex X and going through K and ending in Y. And if we just reverse those arrows, then we lose those paths. Do you see what I mean? I mean, if here a path ends in I and it continues there in Y, we cannot go through K anymore if we preserve the orientation of the arrows. So there is no path from X to Y. They are all lost. And this is too drastic. We do not want that. Yeah, we want to keep that information. There were paths coming from somewhere before I, passing through K until J, and then going further on. So in order to be able to preserve that, we would need to artificially introduce a new arrow, or say we introduce this new arrow here, that allows us kind of to jump over that vertex K. Yeah? If I introduce that new arrow from I to J, then I still have the possibility to consider all the paths from X going to I, jumping over K, and going on to Y. So this is the better notion if you want to reflect at a arbitrary vertex K. That's good so far? So
I
that
have
this
a
is,
question.
yes?
So when we are doing it for sinks and sources, then also this thing what you have told that was going to happen, right? So if
No, I don't think so. So if K is a sink, say, like so, yeah. So there are paths coming from X into I, but K is a sink, so there's no arrow going out.
yeah, so the path
Yeah,
is ending at K at the first place. Now when you apply
yeah,
reflection, the path will end at I, right?
right, yes.
Yeah, I mean, is this not a problem? Because
Now
like
we change the behavior of paths relative to K.
okay,
Sure, because we reflect at K. We have to change this. So paths ending or starting in K, they will be different, that's for sure.
okay,
Yeah.
okay.
But just I don't want to, I want to keep the other paths that are kind of going through K and then continue further on. I want to keep this information.
Right, okay.
Yeah, paths ending or starting at K, sure, they're gonna be changed if we do a reflection at K. Yeah. But I want to keep this kind of local and the global information going from X past K to some other vertex Y. I want to keep this information. Yeah. So this is really my motivation for the following for the definition that follows, and it's not how Fomin and Silivinsky
Um,
explained it to us.
Can I ask a question here?
Yes, sure.
So a priori, we consider a quivers without a loop, but this process will introduce a loops, right?
Yeah, let's look at this in detail. Let me first give the formal definition. So up here, that was just the motivation. Let me now give the formal definition of a mutation, and then we can see what happens. Okay.
Okay, thanks.
So thank you very much. So let's start with a quiver Q that has no loops, no two cycles, and any vertex K, and then we want to define now the mutation. I want to give, they don't call it a reflection, they use a different symbol, mu K, the mutation, because it's kind of different to the reflections. The mutation mu K at the vertex K of the quiver Q is defined as follows. So first, as I said, for every path from I to J, which is passing through the vertex K, we add a new arrow that will be labeled by that path. So the path is the path alpha beta. So we introduce a new arrow labeled by alpha beta. This is just a label, it's a name, it's one arrow. From I to J. Then in a second step, we do what we are used to from reflections. We reverse all arrows that are adjacent to K. So from here to here, that's what we did. We reverse the orientation of alpha and beta. And then now I come back to your question. Then it could be a priori that we created a quiver that does not satisfy our assumptions. Our assumptions was we have no loops, no two cycles. So in principle, my quiver Q could have had an arrow like so from I to J, this one. So if there was such an arrow, then that procedure would produce a two cycle. yeah, I mean that newly introduced arrow with the one which was already existing before, these two would create a two cycle in my quiver, but I said I do not want any two cycles. And therefore the last step is delete all two cycles. So our procedure might have created some two cycles. We have to delete them afterwards, and we need to follow those three steps to have an admissible quiver. Now about loops, we do not create loops. So we how could we create a loop? There were no loops in Q before. Yeah, so they are not present. What would be the possibility to create a loop if we add an arrow like so? Yeah, this arrow would be a loop if I equals to j. Yeah, but how does that happen? How can that happen? How can I be equal to j if there's a arrow alpha from I to k and an arrow beta from k to j? So that would be this situation, and then we would create a loop, as you correctly pointed out. So this new arrow alpha beta would be a loop. However, we said there are no two cycles. So the loop would be created only if we have a two cycle in the quiver before. You see what I mean? I don't know who was asking this question.
Yeah, yeah, I can see this.
So this is a very good point. So in principle, this new arrow could be a loop, but it can be a loop only if it comes from a two cycle. But we said there are no two cycles to start with. Yeah. So our quiver Q that has no loops, no two cycles, will not.
Excuse me, sir. I have a question.
Yeah.
So,
Yes.
if we have an arrow from J to I, then we'll initially add a path alpha beta, but then we'll end up deleting it, so it won't end up in the mutated quiver. Is that right?
Sorry, could you repeat your question, please?
Yeah. So if we have a path from J to I as well, then we'll create a path alpha beta, but then we'll end up deleting it because we can't have two cycles, so it won't end up in the mutated quiver. Is that correct?
If you have a path, any path or a direct, just a length two path?
No, like in point one, the black arrow, if you have drawn
Uh-huh.
to illustrate, so that will create a two cycle. So we'll end up deleting it. So that means
Yes.
that the alpha beta cycle, which we ended up adding, the alpha beta arrow, that won't end
Yeah.
up in the mutated quiver. Is that
Yes,
correct?
yes. This is totally correct. Yes. So that it is really a three-step procedure. I mean, first we add some arrows, then we delete some arrows, and we might end up with more or less arrows than we had before. Yes. So
All right.
let's look at some examples. I hope that clarifies a bit the questions. So first example is the simple example. If we have a sink, then the mutation is just a reflection at this sink. Yeah, because if we have a sink, there's no path of length 2 passing through the sink K, and the only thing we do, so we do not do anything in part 1, we just reverse the arrows, and since we did not add any arrows, we do not need to delete anyone. So the mutation at the sink is just the reflection at this sink. Same for sources. Yeah. So the operation of mutation is really a generalization of that reflection. And let's go to some more interesting examples. So let's say we have this quiver Q, which is a quiver of type A3, 1, 2, 3, and I want to study what happens when we reflect in the vertex 2. So we follow our first step 1. There is a path from 1 to 3. So we want to add this path 1, 2, 3, alpha, beta. So we want to introduce a new arrow, say this one here, and we label it alpha, beta. So that's good. We introduce that. Second, we want to reverse all the arrows adjacent to the vertex 2. So let's do this one. I reverse the arrows. They go backwards now. Perfect. And then I have to delete all 2 cycles. Well, there are no 2 cycles. There's a 3 cycle, but this doesn't matter. 3 cycles are allowed. There's no 2 cycles, so I'm finished. This is the mutation at 2. Okay, that's good so far? Now, let us repeat this process. So what happens if I do another mutation at the same vertex? Yeah, so let's go. I keep my vertices 1, 2, 3. In the first step of the mutation procedure, for each pass going through K, I add an arrow. Okay, so this time there's a path going that way. So I need to introduce a new arrow. So that new arrow will be going this direction. So I introduced this new arrow, you see that? But I had the other arrow upstairs before. And sorry, I skipped one step. I need to reverse the orientation. So let's do that. I reverse the orientation like so. Alpha, beta. And then I have 2 new arrows from 1 to 3 and from 3 to 1, and they form a 2 cycle, and I need to delete this. So I do have to delete that newly formed 2 cycle. You see what I'm doing? I got a message from Teams. So you see what I'm doing? I have to delete those. Let's do that. And this is my quiver. Is everybody okay with that procedure? Yeah? Are you good? So what do you observe? What do you observe? What did we do? We start with a quiver Q. We mutate at a vertex 2, then we mutate again at the vertex 2. The quiver that we get is the same one. Yeah. So what we end up is the quiver Q. And this is a general fact, not only in this example. You can verify that the mutation, the operation of mutation is what is called an involution. This means if I mutate twice at the same vertex, then I do get back my quiver Q. Yeah. Applying mu K once creates a new quiver, twice for that mutated quiver brings me back to Q. So this is an involutive operation. That's good? And we verified in this example. Okay. So I have another example. Good. Do you see my example? Yeah, let's do a little bit a more complicated example. Thank you very much. So I want to start a mutate in any of the 3 vertices 1 or 2 or 3. I let you choose. We do this democratically. Which one do you prefer? Who proposes to mutate at 1? Who says 2 is good, and who suggests we should mutate at 3. So everybody who is in favor of mutating at 1, can you raise your hand or do something? We are voting here. Good, so I have 4 people, 6 people going for 1. That's good. Let's do this. This is okay. Thank you very much. So can you help me? When I mutate this quiver at 1, I do keep the quiver mu1q. I do keep the vertices. Okay? I mutate in 1. That means I have to introduce new arrows for every path of length 2 that passes through 1. So how many paths are there passing? How many paths of length 2 are there passing through the vertex 1? Three of them, according to these 3 arrows. Yeah, 1, 2, and 3. So I have to introduce, first step, I have to introduce 3 paths, and they go in that direction from 3 to 2, right? Okay, so my new quiver will be looking like this. I messed up a little bit the geometry of my quiver, so let's say 2 and 3. So I'm gonna have to introduce, in addition to the 2 arrows which were there before, I have to introduce 3 arrows in the other direction. Yeah? What next? I need to reverse the arrows which are adjacent to 1. Okay. And then I need to delete 2 cycles. Yeah. So deleting 2 cycles is the problem around here between 2 and 3. There's something happened. And we have 2 arrows downward and 3 arrows upward. They cancel each other out. And what is left is 1 arrow going up. That's good? Okay. And then, so this is the operation mu1. Yeah.
Which two we pair up? Is there any convention that pairing up is just blindly deleting? I mean, which way we pair?
It's your choice. What really is important is only the number of arrows between any 2 vertices. I will only keep this information. Yeah.
Okay.
So this is, if these arrows were called alpha, beta, gamma, I can freely interchange them. What is really important for the information of the quiver is only the number of arrows going from 3 to 2.
Okay, thanks.
Yeah. So I can move from the quiver Q to the quiver mu1 to the quiver mu1 of Q. If I apply mu1 here again, then I will go backwards. So this goes back and forth. But I could anytime, I could continue here mutating this quiver in 2 or this quiver in 3, creating new quivers mu3, mu1, Q. And I want to give you the feeling that you create kind of a mutation tree. Yeah, so you start with 1 quiver in the beginning, then you apply mu1 and mu2, or mu1 and mu3, or you apply mu3 and then mu1, and so on and so on. So you go on in all directions. Let's do this one also for a little bit. Let's go down here. Say we want to consider mu3q. So what do I do to compute mu3q? So first I copy my quiver, I put it down here, and so here we go. So first thing, we mutate in 3. I need to see how many paths are there of length 2 from 2 passings through, how many paths of length 2 are passing through the vertex 3? How many paths are there? 6. Thank you, Amit. So this is kind of getting a lot. Yeah, so I have to add 6 new arrows. You see what I'm doing? I have to add 6 new arrows going this way down, and I cancel them with the 1 arrow that exists here. So I'm gonna end up with 5 arrows in that direction, and let me label this just 5. So there's 5 arrows. I don't care about their labeling, okay? So the number of arrows going from 2 to 1 is 5, which is 6 minus 1, because there was 1 arrow before in the reverse direction. So this is how we do it. That's okay? And then in the second step, I need to reverse the direction of all the arrows that are adjacent to 3. Let's do this. So there's 2 arrows going up and 3 arrows going down. Maybe I write this directly as 3 arrows going down here, and there were 2 arrows going up. So this simplifies the notation a bit. Okay, so, and I did I deleted my 2 cycles already. This was 6 minus 1. And so this is how I can continue. So you do see I could continue now mutating this one here at 1 and this one here at 2. So you do see in general that I might create many new arrows. Yeah. And so I got a question in the chat. I said a mutation tree. I was not very accurate. This is good. There will be relations among the mutations, and I want to ask this question I want to discuss this very question in the tutorial afterwards today. Okay, this is a good point. So a priori, we start with a tree. We go out away from the original quiver, but then there will be some identifications. There will be some quiver isomorphism that say the mutation mu1, mu2 equals up to isomorphism of quiver, the mutation mu2, mu1 of Q. So there will be in general some identifications, and this is in fact a difficult problem. Yeah.
Thank you. Thanks a lot.
Thank you very much for this question. And you see that the combinatorics of those mutations starts getting a bit complicated, and therefore Bernhard Keller has created an app, a mutation app, and this is very nice to do. How can I switch my sharing? Okay, I stop the sharing and then I share again with a new window. Okay, so I stop it, and then I gonna try to share a new window. So let me see where's my Teams. Share content. Window here. Okay, do you see my?
Yes.
Do you see my quiver? So you can just Google quiver mutation. There's an app that Bernhard Keller wrote, and it gives you a quiver like this, and you can really, I invite you to play around. We can also do this in the tutorial later. In this arrow, you can add nodes, you can add arrows, you can delete nodes, and so on. You can move those arrows. That's very good. And we can play around by clicking on one vertex. We apply a mutation in that vertex. So let me click on vertex, say which do you want? On vertex 10, click, we apply the mutation. I go back, I got the original one. So can we analyze this? Do you see my mouse? Yeah. So if I mutate on 10, there was a path from 6 going through 10 to 9. So I add an arrow here, but there was an arrow in the reverse direction. So if I apply the mutation, this arrow disappears. That's fine. Yeah. And I can mutating in 1, I make this arrow disappear. I mutate in 7, I make this arrow disappear. And then it starts getting more complicated. Let's do mutation in 5. Okay, that looks complicated. How is the quiver? I don't know. Maybe we can visualize it better if I move those guys over there. It's not getting really nicer. Let's mutate in 7. This is good. Mutate in 5 again. And I don't know. So you can play around and see a little bit what's going on. If I play around with that mutations, then you see, suddenly I created an isolated leaf in the quiver. So I created actually a sink or a source here. And you can also randomly do 15 mutations and see what's going on. And you see that the number of arrows does not explode. So in fact, that particular quiver is what they call mutation finite. So in principle, the number of arrows can grow to infinity. Yeah. But there are some quivers who under mutation, whose class of quivers which are equivalent under mutation is a finite class, and this is one of those particular cases. And Bernhard Keller said there are 5,739 quivers that can be obtained from our original quiver using mutations. I will not produce all 5,000 right now. You can play around a little bit with it and see what happens. So if I add some arrows, if I add an arrow from 1 to 4, then you see the notation. I have 2 arrows here, yeah. And if I add this arrow, then things start to change, yeah. I mean, if I apply now my mutation algorithm, then I certainly start getting more arrows. What happens? I'm getting suddenly more arrows between different vertices. I cannot really create the effect that I want to see. I repeat randomly. You see what happens? Now I have 18 arrows between 4 and 1 and 12 arrows between 4 and 3. And if I repeat random mutations, I create more and more arrows. You see what's happening? So the whole thing explodes. So the representation, there are quivers whose iterated mutations will create infinitely many arrows. And the page is unresponsive. I crashed the system. I'm sorry for this. I can stop this. There's a nice app and you can do this yourself. I invite you, just Google quiver mutation and you will find it. That's good. Any questions to this? No? We are good? Okay, good. Then I would like to share my iPad again. You see my iPad? Okay. So as I said, there's this Quiver mutation app. Please have a look at it. And I use the notation I used already that I call two quivers mutation equivalent, Q and Q prime, if there is some sequence of mutations that transforms Q into Q prime. And we are generally interested in the mutation class, in the mutation equivalence class of a given quiver, and that can be finite or infinite. And I gave you some cases where it's finite and other cases where it's infinite. Good. So now I want to formalize the things a little bit in the way as Fomin and Seliwinski had actually formulated in their paper. So in Fomin and Seliwinski's paper, they did not start using quivers. They did not start using skew-symmetric matrices. They actually started using skew-symmetrizable matrices. So this is my next step. But for now, let's talk about skew-symmetric matrices for a moment. Okay. What is a skew-symmetric matrix? This is a matrix. I consider matrices which are square matrices, entries are integers, and such a matrix I call skew-symmetric if its transpose is negative of the matrix. Yeah. So we transpose it, then we change the sign. We get the opposite sign. This means in particular you have zeros along the diagonal. And as a first result is the observation, how can we compare this to our notion of quivers? There's in fact a bijection between quivers and skew-symmetric matrices. I can realize everything that I'm doing, all the quivers, I can realize it as skew-symmetric matrix. And how is this done? This bijection, if I have a quiver Q given, so say Q is my quiver here, and I want to attach to this one a skew-symmetric matrix BQ, so that map here, Q goes to BQ as symmetric matrix. This is defined as following. Starting with the quiver, we define the matrix which has entries Bij, and we just put at the entry Ij the number of arrows from I to j minus subtract the number of arrows in the reverse direction. Yeah?
May I ask a question?
Yes, please.
Yeah, so by your assumption, so at least one of these quantities should be zero, right? Because we don't have two cycles.
Exactly. If we start with a quiver that has no two cycles, that it cannot be that both of these numbers are non-zero. Yeah, so one of the numbers will be zero, and then we either take the number of arrows from I to j, or if we are in the transposed matrix, then we take negative the number of arrows from j to I. Yeah. And however, you see immediately here in our mutation process, we do create some two cycles, and that formula deletes them automatically. Yeah. I mean, if there's a two cycle, there's some arrows going from I to j, some arrows from j to I, and in the matrix notation, they cancel each other out right away. So that step is done automatically if you use matrix notation. In this sense, the matrix notation is more convenient. And I ask you to look at the inverse map in the tutorials this afternoon. And let's do some little examples. Examples, suppose Q is the quiver 1, 2, 3. What is the skew-symmetric matrix associated to this quiver? I do have an arrow alpha from 1 to 2. So from 1 to 2, B1, 2 will be an entry 1. There's an arrow beta from 2 to 3. So from 2 to 3 in the entry 2, 3 of the matrix, there's an entry 1. There's one arrow. And in the reverse direction, there's how many arrows from 2 to 1. There's an arrow in the reverse direction. So from 2 to 1 in this entry, B2, 1, I write a negative 1 because there's an arrow in the reverse direction. And same thing here, I write a negative 1 from in the entry 3, 2 of the matrix. And everybody else is 0. All the other entries are 0. And this is the matrix. This is a nice skew-symmetric matrix. If I kind of reflect here along the diagonal, I get the negative of this matrix. So BQ transpose is negative BQ. And this is how I can encode the quiver. Yeah. More generally, if I have a more complicated quiver like so, I would have one arrow from 1 to 2. I would have 2 arrows from 2 to 3. And from 3 to 1, I have got 3 arrows. And then I just fill it up symmetrically with an opposite sign, and I do get my matrix. So there's really a nice bijection between skew-symmetric matrices and quivers. The entries in just a second. The entries in the matrix are integers according to the number of arrows, and the sign only indicates the orientation. The sign in the matrix is only used to indicate is the arrow oriented from I to j or from j to I. Yes, question?
Yeah, sorry. So I'm actually a bit confused. So, for example, if you take two quivers, so one is, I mean, both are with two vertices, 1 and 2. One is disconnected. I mean, there is no path between 1 and 2. And for the other one, yeah, one is this, and the other one is you have a 2 cycle between 1 and 2.
Yeah.
Yeah. So
And
don't they have same matrix?
They have the same matrix, yes.
But then
So
how
the
would you
matrix,
get rejection? Sorry.
the matrix would be the same because they cancel each other out. So when I formulate my lemma, there's a bijection between quivers. I always assume, this is my standing assumptions, when I say quiver today, then this is a quiver that does not have loops nor two circles.
Okay, thanks. Yeah.
Yeah, that bijection would not work for two cycles, and I would have a real problem kind of encoding the orientation of the arrow by just one integer entry and its sign if I do allow two cycles. This bijection does not work for quivers that have two cycles. Yeah. So I here really need that assumption that we made somewhere in the beginning. The quivers we consider, they do not have loops nor two cycles. So the quiver here is not allowed. We do not consider this quiver, right? Are we considering quivers which are not connected? Yes, sure, they don't need to be connected. I could change to this quiver, and if I change to that quiver, then I would just replace from 2 to 3 by zeros. So connectivity is not something that is really important. Quivers correspond to skew-symmetrizable matrices. That's good? Okay. So we modeled quivers without loops or two circles by skew-symmetric matrices, square matrices, entries in the integers. So of course, for the quivers, we defined a mutation. Now you ask yourself the question, what is the mutation in terms of the matrices? Yeah, I mean, there's a bijection between quivers and matrices. There's a mutation on this side. Of course, there's a mutation on this side of the matrices. How does that look like? So let's say we have a matrix which is skew-symmetric. We fix a number k between 1 and n, and then we want to define the mutation mu k of b. This is given by the matrix mu k b, which has entries bi prime, bij prime, and here is the formula. Okay. The formula looks a bit more complicated than the intuitive description of a quiver mutation. The quiver mutation has more the flavor. I add, I delete arrows, I reverse arrows. But it's the same thing. I mean, the two things, quivers and skew-symmetric matrices correspond to each other bijectively, so it must be the same thing. And it's just, if you implement it on a computer, this is what you would implement. Yeah, for a computer, that is easier. For me, the quiver mutation is easier, but they are the same, they are equivalent. Yeah. So if we want to understand what's going on, how do the entries of the mutated matrix, how do they change? So the new entry bij is just the negative of the entry before if I have if I consider, say, arrows from I to j or arrows from j to k. So adjacent vertices, adjacent arrow change the direction. In the matrix notation, they change the sign. This is the same thing. Yeah. So this was our reflection. Arrows adjacent to k change the orientation. They change the sign. What happens to the other arrows? Well, first we keep them, but then we're gonna have to add new arrows for every path that goes from I to k and from k to j. So this is encoded by that product here. And but I only want to consider paths that go in really the direction from I through k to j. So if that product here is negative, I don't add anyone. I add only if that is a positive number. Therefore, I do this maximum of 0 and that number. I need to make sure the sign is correct. And then if I add this to the arrows which were before, in the matrix notation, this sum is really the cancellation of two cycles. Yep. So if there were some arrows in one direction and some arrows in the other direction, they cancel each other out. You just take the sum of these two entries. This is the same thing. This is the matrix mutation. So the matrix mutation of the skew-symmetrizable matrix B is really the matrix that you obtain from the mutated quiver. These two operations are compatible with each other. And you can choose your preferred way. You mutate Quivers or you use this wonderful formula as you wish. That's good? Okay. How much time? I've got how much? Half an hour?
Yes, yes, half an hour. Yeah.
Okay. And I just continue, no break. I just go on the last half an hour. Is this okay with everybody?
Yeah, that's what we have been doing for past 2 weeks. Yeah, you can.
Good, good, good. I drink something and then I'm with you. That's good. Okay, perfect. So we do know mutations of Quivers. We studied mutation of skew symmetric matrices which correspond to Quivers. And now let's take a step back. We were considering the Dynkin graphs, so the A, D, E type Dynkin graphs, and the Dynkin quiver. So Dynkin quiver is one whose underlying graph is a Dynkin graph. But you have seen in the part on Lie theory that there are more Dynkin diagrams than the simply laced ones, more than the ADE types. There are more Dynkin types. So there's the Dynkin types B and C and F and G, yeah, and they cannot be directly realized by those quivers, yeah. So in order to consider the other Dynkin types, the non-simply laced ones, the types B, C, F, G, we need to enlarge our notion of a quiver. We need to enhance our notion of a quiver. And the enhancement is given by a so-called valuation. A valued quiver is now a pair, a quiver Q and a function V, which is called an evaluation. So Q is a quiver without loops. And we do assume that we have at most one arrow between any two vertices. So let's start with such a simple quiver, yeah, no loops and only one arrow, no parallel arrows. And then the evaluation is a function that associates to every arrow a pair of numbers, two numbers, yeah. And we do assume that there exists another set of numbers di, which are called the symmetrization of the quiver. And those numbers should satisfy that for every arrow, if we take the first number attached to this arrow, v alpha 1, and the second number attached to this arrow, v alpha 2, and if I then do multiply with these numbers di attached to the vertices I and j, then I do get equality on both sides. Good, this is a bit not so easy, the definition. Let's give us some examples, right? So let's see the Dynkin diagram of type B3. How can it be modeled using a evaluated quiver? So in B3, I have something, I mean, here's the type Bn. I have something kind of a fancy edge between 1 and 2, which has some labels. So I would, as a valued quiver, realize it as follows. The valuation of the arrow from 1 to 2 is got 2, 1. And if I don't write anything, then I mean it's 1, 1. Yeah, so the arrows labeled 1, 1, I don't attach the label. So when you see a simple arrow, then this is always supposed to be 1, 1. I don't write that. And only the non-trivial valuation I do write. So B3 would be the labeling 2, 1, and C3 would be given by the labeling 1, 2. We can do that. And what about that numbers D here? Yeah, I mean the numbers D should kind of balance this in. They are not equal. The weight is not equal, and the numbers D should kind of balance this out. So if I multiply 2 by 1 and 1 by 2, then in the product I get 2, 2. I have the equality that was requested here. Yeah, there's just a way to give a different weight to the vertices such that when we multiply by those weights, we do get equal weight left and right. Yeah. So this is the role of this D. In C, I would multiply vertex 1 by 2 and vertex 2 by 1. Then in the product, I get 2, 2. It's balanced. It's equal. Yeah. So that's what we do. The type G3, you would have a 3 and a 1, and then the corresponding symmetrization would be a weight of 3 at vertex 1 and a weight of 1 at vertex 2. So we do get 3 times 3 is 9 and 1 times 1 is 1. This is not equal. Okay, forget that. I would like to do D is 1 and 3 here. Now it works. Yeah. 1 times 3 equals 1 times 3. Good. Okay, so there's a notion of a valued quiver. There's also a more generalized notion of a skew-symmetric matrix. This is the notion of a skew-symmetrizable matrix. Okay, a matrix B with integer coefficients and square matrix is called skew-symmetrizable if there is some diagonal matrix given by diagonal entries d1 up to dn, positive integers, such that the product of B with this diagonal matrix is a skew-symmetric matrix. So that's kind of what we did in these evaluated quivers before already. So suppose I'm in that example, in that example, G2 is given by the evaluation 3 and 1. And let's look at this corresponding matrix B. Say the matrix is 1 and negative 3. Okay, 1 and negative 3. I'm a bit in conflict with what I did here. So let's look at this matrix. If I multiply this matrix with a diagonal matrix with weights 3 and 1, then DB would be the matrix 3 and negative 3. Is this correct? Did I do my matrix product right? I multiply the first line by 3, so I get 0, 3. And the second line I multiply by 1, so this is negative 3, 0. So this matrix is skew-symmetric. And that's what I want. A matrix is skew-symmetrizable if I can multiply it by a diagonal matrix such that the product is skew-symmetric. Good. And kind of the this valuation and that's diagonal matrix D, they play the same role. So in fact, we can find a more general version of our lemma 1. And in fact, there's a bijection between valued quivers and skew-symmetrizable matrices. Yeah, so this is similar to lemma 1. Just now it's a more general context. I can do valued quivers or skew-symmetrizable matrices. And this is the context, skew-symmetrizable matrices. This is the context, if you go to this famous first paper by Fomin and Sliwinski, this is how they formulated cluster algebras. They start with a skew-symmetrizable matrix. And there they implemented their mutation rule. Definition 2 is our mutation rule. So that's the mutation rule. You can do all what we did before, the mutation, you can do all that in the context of skew-symmetrizable matrices. This is how Fomin and Sliwinski defined it. They gave this formula for the mutation of a matrix, apply it to the context of skew-symmetrizable matrices. And if you wish, using this bijection, you can translate that mutation rule back to a mutation of valued quivers. Yeah. But really, Fomin and Sliwinski, that's how they started mutations of skew-symmetrizable matrices, and they defined their cluster algebras in that context. So just a little remarks, question?
Yep. So I mean, in the valued quiver, if you mutate some vertex, let's say, and you introduce new arrows, so how do you put the value on those new arrows?
This is a good question. I invite you to study it in the tutorials. Yeah, sure. I'm not gonna mutate too many valuated quivers. I really here go for the skew-symmetrizable matrix. I mean the mutation rule here is clear. it is that rule. And then you just have to figure out how it plays out for the corresponding valued quiver. Yeah.
I have a question.
Yeah.
So like you can view skew-symmetric matrices as skew-symmetrizable matrices by taking the
Sure.
diagonal matrix to be
1,
identity.
1, 1, 1, 1. Yes.
Yeah. So what is the corresponding thing for valued quivers? I mean, how can you view a quiver as a valued quiver? I mean, will you just do it
You
like
do
1,
you do
1?
1, 1 everywhere.
Okay, fine.
Yeah. So if you have your original type A quiver, you do 1, 1 everywhere.
Okay.
Then this is a valued quiver. So valued quivers embed into valued quiver by the trivial valuation 1, 1, 1 everywhere. And same thing for the diagonal, for the skew-symmetrizable matrices, you put ones in the diagonal everywhere and all works fine. And this is just to say there is a more general context, and this is the context that Fomin and Seliwinski were really studying. So just to wrap this story up, the Dynkin graphs correspond, I mean, all of them, all Dynkin graphs correspond to root system, correspond to semi-simple Lie algebras. Dynkin graphs are given by valued quivers. We considered in week 1 only ordinary quivers. These are quivers where all valuations are 1, 1, and they correspond to the simply laced root systems, the root systems of type A, D, E. Yeah. And the simply laced root systems, for instance, A2, the quiver type A2 corresponds to this root system. I don't know, you have done this comparison in week 1, right?
Yes.
And the type A2 root system has two simple roots, alpha 1 and alpha 2, but it's really given as a root system by a hexagon. I mean, by 6 points in the 6 points in the plane, which form a regular hexagon. So in particular, the two simple roots both have the same length, yeah. And you saw in week 1 there's a bijection between the positive roots and the indecomposable representations of this quiver. So the simple root alpha 1 corresponds to the simple representation in 1, the simple in 2, the simple representation in 2, and then there's this one large root alpha 1 plus alpha 2, which corresponds to the indecomposable, which is one-dimensional at both vertices. So we have seen this. And you can extend all this. I'm not going into the details of that. I just want to tell you there's a generalization of all that goes into valued quivers and non-simply laced root systems. So for instance, if we take the Dynkin diagram of type C2, which is a valued quiver with values 1 and 2, this corresponds to the root system of type C2. C2 and B2 are the same root system, but this is a root system which is given by 1, 2, 3, 4, 5, 6, 7, 8 roots. And the two simple roots are alpha 1 as before, and now alpha 2 is that one, yeah? And they form a square, yeah? I mean, these, they lie on the unit square, yeah? So the root alpha 1 has length 1, and the root alpha 2 has length square root of 2, yeah? And then you get the other roots by alpha 1 plus alpha 2 is this one, and the third positive root, the fourth positive root is 2 times alpha 1. So alpha 2 plus alpha 1 plus alpha 1 gives me this one. So there's a similar story. You could still obtain a bijection between the positive roots in the generalized context and indecomposable representations of valued quivers, but you would need to introduce what that actually is, a representation of a valued quiver. And to obtain something similar as we had here, the simple roots correspond to the simple representations, and there are other roots that correspond to representations in the composable ones. You would need to do one crucial thing. The fact that there's a valuation between 1 and 2, the fact that the roots do not have the same length, this need to be modeled by taking different fields. And in that particular example, you would need to model it by a field extension of degree 2. So you can say vertex 1 has value 1, so you put the real numbers here. Vertex 2 has value 2, so you put the complex numbers here. And the dimension of the complex numbers over the reals is 2, and that corresponds to the square of the length of that root. Yeah, alpha 2 should still correspond to kind of a simple representation, but it should have sort of a different length. It should have kind of a different dimension. So if you model the whole thing by a field extension from R to C, then you are able to realize different fields, and a field extension of degree 2 allows you to model representations of that quiver. Now, if you have more complicated things like this alpha 1 plus alpha 2, then you need to start mixing up the two fields. So you have the reals here and the complexes here. And the question, what is this thing here in the middle? Here things start getting complicated. Yeah. So this is not a representation of one quiver that doesn't fit into the context we did in week 1. You would need to consider whatever is here, you would need to consider this as a bimodule from the left by the reals, from the right by the complex numbers. So we kind of fix reals on 1 and complex numbers on 2, and then we consider RC bimodules. And so that would be, this one here would be a bimodule over R and C, which has kind of real dimension 1 here and real dimension 2 here. That would kind of correspond to this root. And but if you want, anyway, there's a whole machinery of considering representations of valued quiver, which are also sometimes called representations of species. I will not go into the details of this. I just want to tell you, Fomin and Zeliwinski defined their cluster algebras for skew-symmetrizable matrices so they can deal with all Dünkin types, the simply laced ones, ADE, and the non-simply laced ones, BCFG. And there's a parallel theory of valued quivers and of valued quiver representations that allows you to deal with that. But we didn't go into this in week 1, and I will not go into this in the third week. Yeah. For G2, what field extension of R can we expect? We need to have a degree 3 field extension. So from R to C doesn't do the job. Yeah, you will need to go into Galois theory, give yourself a field extension of degree 3, such that the larger field has dimension 3 over the smaller field. And for all those reasons, I will not do the details of this. Yeah. But we do need to allow field extensions of degree 3 to model the G2 type root system, definitely. Yeah. Okay, that's good. And then, so let's leave it there. So I have got 10 minutes. I'm kind of behind in my schedule. I will pick up tomorrow again. We did not define, excuse me, we did not even define what is a cluster algebra so far. Let me go through this quickly, and I will start from there tomorrow again. A cluster algebra. So far we did only talk about mutations. So a cluster algebra is given by the following things. So first, we want to consider the field of rational functions in n variables with rational coefficients. So let's consider the field F of rational functions, quotients of polynomials in the variables x1 to xn. We call seed a pair of two things, R and U. R should be a quiver. If you want to do the more general story, you can take a valued quiver with n vertices, and U here is a set of n independent elements in this field. You could, for instance, take x1 up to xn. Yeah. And then we want to define a mutation at a vertex k of that datum of a seed. A mutation of a seed will be a new seed R prime U prime, where the quiver is obtained from the quiver R by mutating the quiver. This is what we have discussed. And now we have to introduce what is the mutation of those variables. Okay, so let's do this. The new sequence, the new set of variables is obtained from the old one by keeping all variables except the variable number k, and we replace variable number k by a new variable uk prime, satisfying the following relation. The product of uk with uk prime should be the product of all variables u whose index is given by the tail of an arrow alpha if the arrow starts in k, so this is the mutation in k, plus the product of all variables whose index is the start of an arrow alpha if alpha is an arrow that ends in k. So the arrow alpha goes from the start of alpha to the tail of alpha in the quiver notation. The same formula in matrix mutation is given by this formula. And I will use more the quiver notation. I will do an example in a minute. Yeah?
Sorry. Here by independent you mean algebraically independent, which generates the
algebraically independent, yes.
Thank you.
Thank you, yeah. Upendra, where is the valued theory written? This really goes in, there's a sequence of papers by Lab and Ringe, which they consider, which they call representations of species, and species are really bimodules over quivers, and it's complicated. I'm sorry to tell you. Okay.
Thank you.
I prefer not to go into the details. So there's a bunch of notation, and I will repeat this tomorrow, but I just wanted to get this out today already. So we considered the field of rational functions in n variables. A seed is a pair of a quiver and a set of n independent elements. A mutation is defined as the mutation of the quiver and a mutation of the variables where we replace the case variable by a new one, and that new one is defined by this equality. I will do an example in a minute. The cluster variable to define cluster algebras, we need to specify where do we start our process of mutations. This is called the initial seed, and the initial seed is the initially given quiver Q, and the initial variables are just the variables x1 to xn, and then we're going to mutate them. A cluster is each of those sets of n algebraically independent variables that are obtained by mutations of seeds. The cluster variables are all variables that are obtained by iterated mutations. So everybody that we produce along the way is called a cluster variable. And the cluster algebra finally is the algebra, the subalgebra of this field generated by all the cluster variables. And the exchange graph has vertices, all the seeds, and the edges are given by mutation. So this is a bunch of notation, and I would really start illustrating this by some examples, and we're gonna continue tomorrow. Yeah. Amit, I got 5 minutes.
Yes, yes. Yeah.
Okay, so
You
let
can
me
take
let me
6. Yeah.
let me do one example at least. Let me start with one example at least. So the quiver of type A2. It doesn't get simpler than this. Okay, so the initial seed is this quiver and the two variables x1, x2. The mutation mu1, I did not want to give you this. The mutation, first we mutate the quiver. If we mutate the quiver, we reverse this arrow, so that's easy. How do we mutate the variables? We say, in that set of variables, if we mutate in one, we keep the second variable x2 and we replace the first variable x1 by a new variable x1 prime, such that the product of the old and the new variable is given by the product over all variables whenever there is an arrow alpha ending in k. Is there any arrow ending in 1? No, there's no such a thing. Yeah. So if there's no arrow ending in 1 and I mutate at 1, then this product here is the empty product, and the empty product by convention is just 1. So I write here a 1. You see what I do? This was the empty product. Yeah. Then plus the second product is given by all arrows. What did I say? The start is, did I mix this up? I take all arrows that start in K. Sorry. There is an arrow starting in K, alpha. There's an arrow starting in 1, alpha. So that's not what I do. There is an arrow starting in 1, so this is my K. There's an arrow alpha starting here. So this is the start of alpha, this is the tail of alpha. So I take the product of all variables whose index is given by the tail of alpha. So I have x2 here, right? And then if I go into the second part, now I consider all arrows whose tail is k, but there is no arrow ending in 1. So the second product is the empty product. For the second product, I say this is 1. Sorry, I got this right now? Correct? So I have that, what I call exchange relation. And to introduce the new variable, I would like to write the new variable as an element in this quotient field. So I write it as say, as 1 plus x2 over x1. I just bring the x1 on the other side and I write it as a rational polynomial. So this is my new variable. So my new my mutation really from this seed into that seed mutates the quiver. 1, 2 is replaced by 2, 1. I reverse the direction of the arrow, right? And the mutation of the variables is that I replace the first variable by this new variable, 1 plus x2 over x1. Now this is my new seed. Yeah, this is the seed mutation. This is my new seed. And seed mutation is going to be an involution. So if I mutate that seed, I go back to this seed. And now I can continue doing the following mutations, but I want to do this tomorrow. That's good. So we have seen the definition of cluster algebra. Whew, I'm happy, but at this moment it's not clear, and we need to study more examples. We're gonna do that tomorrow. Thank you very much.
Yeah, so did you use the values? So the definition was about valued quivers, right?
Yes.
Yeah. Did you use the values in defining the mutation?
Yeah, this was hidden. This was hidden in the matrix. I mean, the skew symmetrizable matrix, the values are encoded in the coefficients of the matrix. So they are here. For valued quivers, look at this formula.
Okay. Okay.
So that was the formula for a quiver, non-valued quiver. So this formula here was for non-valued quiver, or trivial quiver with trivial valuation.
Okay. Thank you. Thank you. Thank you.
Any other quick question?
I wanted to say a small thing. Like when you talked about the inclusion of quivers as valued quivers, like quivers can have multiple arrows between two vertices, while valued quivers cannot. So you need the map to be like n, where the n is the number of vertices. Like
So if you have the quiver like so,
yeah, then the valuation should be 2, 2. Like on
this is the
1 to 2.
quiver
Yeah.
like so. Yes.
Yeah.
Yes, you're right. Yeah.